that's serving a large number of web clients, this kind of disruption may not be acceptable. Another reason is the unreliability of the software patches. The software patches can become unreliable, and this is not because the patch testers are not doing their job. It's really because that software patches are inherently difficult to test for, simply because a large number of machine configuration settings, newer versions of DLLs, and so on. So it's quite reasonable that for a particular machine configuration, the patch that's released breaks your system. And when that particular patch breaks the system, it's also hard to reverse that patch. So that's the irreversibility problem with the software patch. The reason is that you have been applying changes to our system after applying that patch, and those changes may be dependent on the patch. So undoing this patch is a non-trivial task. Lastly, because of these top three reasons, technical issues with software patches, it's not really possible to enable complete automation of the patch installation. So the user is in the loop, and oftentimes the system administrators they do a set of comprehensive testing of the patches they receive before they actually encourage their users to install the patches. So when the user is in the loop, there is an unawareness problem. The user may not be aware that their systems are vulnerable and are in need of patches. So you may wonder whether the existing firewalls are effective for the protections of these security network exploitable security hosts. The answer is not really. The existing traditional firewalls, they're typically very coarse-grained. And for example, you block a certain port when there is an incident of a large-scale worm attack. So this will incur very high false positive rate and causes severe disruption in the services. And also, the traditional firewalls are typically placed in the network, and it's a basically one-size-fits-all solution. It's trying to protect all the computers in this network. Some of the computers do not really need the protection because they have already applied their patches, and while the others do. And also, there's this lack of application awareness. Furthermore, it misses end-to-end encrypted traffic such as IPsec. So recently, there is the emergence of exploit-driven attack, exploit-driven firewalls. Basically, these firewalls try to filter according to some attack pattern using a pattern matching or a regular expression. However, this kind of firewalls are vulnerable to attack code obfuscation. For example, polymorphic attacks can evade such firewalls very easily. Furthermore, the worms can spread really fast, and we all know that Slammer overtook the internet in 10 minutes, and researchers have developed newer lower bound, within seconds, the whole internet can be overtaken. So this poses a significant challenge for exploit-driven firewalls. This requires these firewalls to do real-time signature generation and distribution. So our approach is Shield. Basically, Shields are unhost-based firewalls and using vulnerability-driven filters. Our goal is to protect the time window between vulnerability disclosure and patch application. Our approach is to characterize the vulnerability instead of various exploits. And we use the vulnerability signature for unhost-based firewalling. So Shields combine the best of both of software patches and firewalls. Like patches, Shield is vulnerability specific and is independent of the variations of the attacks or exploits. But unlike patches, patches are at the code level, patching the executables, making deployment and testing very complicated. And Shield takes the advantage of the firewall being at the network level and is data-driven. However, unlike the recent exploit-driven firewalls, it's vulnerability specific, and it's not exploit specific. So the advantage of Shield is really that Shield offers as good protection as software patches, being resilient to attack variations, unlike exploit-driven firewalls. And at the same time, it's easier to test and deploy and more reliable than the software patch. So this slide shows an overview of the shield usage. So basically, we envision that shield will be enabled on every single desktop machine in the future, hopefully. And whenever a new vulnerability is discovered, a new shield policy encoding this vulnerability signature is distributed to every end host. And at that time, the protection for that vulnerability is enacted. So essentially, shield intercepts vulnerable application traffic above the transfer layer. This is actually a key advantage of shield because shield only needs to intercept the vulnerable application traffic. For the rest of traffic, it does not need to do anything. It does not need to do any deeper inspection. And the policy distribution is very much like the antivirus signature model. Basically, the virus signature, instead of a virus signature, we distribute a vulnerability signature to every single end host, and resulting in automatic, non-disruptive basically addressing those deployment concerns in a software patch. So this kind of distribution installation model is automatic, it's not disruptive, and it's easily reversible. So we also conducted some study over some of the security vulnerabilities in 2003 and to see whether there's a case for shield, what vulnerabilities can be shielded. Basically, there are 49 vulnerabilities from Microsoft Security Bulletin Board, and out of these 49 vulnerabilities, 12 of them are warm exploitable. Basically, they can be, it's like a network traffic exploiting, say, a buffer overrun in the backend server. Well, all these kind of vulnerabilities, shielded can be easily, shield can provide easy protection. Basically, shield is very good for network exploitable security goals. Shield is endpoint based and is above the transfer layer, so we don't have to deal with IPsec encrypted traffic. You may wonder, okay, how about SSL? In that case, we would advocate building shield on top of SSL. Nevertheless, application-specific encryption will be difficult because we don't have the access to the payload, encrypted payload. So I have just given you a nutshell on what shield is. And next, I'm going to delve into the next level of detail in the shield design. And I'll give you analysis on our design, and I'll tell you more about our actual implementation prototype, some initial evaluations. I'll talk about related work and conclude at the end. So at the heart of shielding is really how we can model the vulnerability. So basically, the intuition behind shielding is really that the worms, like in the network traffic, there's some malicious network traffic speaking some application level protocol, exploiting some service running on your system. So all application level protocols in practice can be modeled by a finite state machine, like this one. At a particular state, you receive a message, you do something, you advance to the next state. Okay, because we're here addressing known vulnerabilities, we know exactly at which state the exploit events can happen. So now I'd like to circle this part of the state machine. This really represents the vulnerability state machine. So this really represents all the possible sequences of the network messages that can lead to the exploitation. Just to make the picture complete, within each protocol state, there's fine-grained application implementation state machine, encoding some application logic, like file being opened and stuff like that. But we're not really so concerned about that part of the logic. We're in the network, we're observing the traffic passing by,